Welcome to Pre-Calculus. Today we will investigate writing and graphing linear inverse functions, focusing on algebraic techniques to create an inverse and graphical strategies to confirm that a pair of functions are, in fact, inverses of one another. So we want to write, we want to graph, and then we'll use our graphs to make sure that they are inverses. We'll take a look at three examples. So our first linear function is f of x equals 1/9 x plus 4 over 9. So the first task is to take this linear function and write its inverse. So let's do that here to the right. I'm going to pick up the pen, and the first thing that I'm going to do is I'm going to switch out f of x with y. So I'm going to write the original as y equals -1 over 9 x plus 4 over 9. Now the reason I switch out f of x and y is because I want to reduce the clutter, because at this moment I'm going to create the inverse by switching x and y. One way to think of an inverse is it's really swapping the domain and the range of a function. So what was our domain x is going to become our new range, and our old range y will become our new domain. So I'm going to make that change. And the way that'll look is now x equals -1 over 9 y plus 4 over 9. So my first step is to switch x and y. Once I switch x and y, I want to now solve for y. Now, to do that for this question, I'm going to start by moving the constant term. So that's this plus 4 over 9. Again, I'm trying to solve for the y. So there's really two things to move, a constant and a coefficient. So I'm going to subtract 4 over 9. And that will cancel here on the right. So that constant term, you will always be able to either add it or subtract it to cancel it. It shows up here on the left side. So that my next step is going to be x minus 4 over 9 equals -1 over 9 y. So one more step to solve for y, I need to get rid of this coefficient -1 over 9. So a good strategy is to multiply by the reciprocal of this fraction, -1 over 9. So I'm going to multiply by -9. I could think over 1. And what that will do on that right side is that the negatives will multiply to create a positive, in effect canceling each other out. The 9 divided by 9 will cancel, and 1 divided by 1 will cancel. So all it leaves here on the right side is 1y. And notice that 1 can basically go away since it's the multiplicative identity. And that really is just y now. So what happens on the left side is really going to finalize my linear inverse. So I'm going to put parentheses because I got to distribute. And I'll just use -9 on this side. I don't need the 1. So that multiplies to both terms and becomes -9x. And then -9 times -4 over 9 is going to have a cancellation with the 9s, and it's going to become +4. And to just finalize that form, I want to switch it around so that it has the slope-intercept form. Y on the left equals -9 over 1. I'm putting that as the slope to help with graphing, x plus 4. One way that I can indicate that this is the inverse is by switching back to the f of x notation. And the way to say that this is the inverse of f of x is to include the -1 exponent. And we read that the inverse of f of x equals -9 over 1 x plus 4. So that last form there identifies this as specifically the inverse of f of x. So that completes the first task. We wrote our inverse function. Now I want to graph both the original and the inverse on our coordinate plane. So these are both set up as y equals mx plus b equations. Just to line that up here with the original, looks like my slope is -1/9 and my y-intercept is 4/9. So I'm going to graph it using those two features. So 4/9, it has the value of about 0.44444. It's a repeating 4. So I'm going to estimate where that is here on the y-axis. That's my y-intercept. And then using the slope, I want to count down 1. So that's going to take me to that place on the y-axis, about the value 0.56, -0.56. And then I'm going to go 9 to the left. Now my graph only goes 6 over, so I'm going to have to estimate 3, 4, 5, 6, and then 7, 8, and 9. So there's my second point there. I'm going to erase these intervening marks. And we're ready to graph the original. So this is the first linear function. It's a very flat function, almost horizontal. And I see that I've gone the wrong direction. Do you see what kind of error I've made there? It's easy to fix, but that would have been positive slope if I go down and left. Let me fix that before I graph it. To get the correct slope, I should go down 1 and then 9 to the right. Glad I caught that. So we'll just count out there 6 plus 3. And then I'm going to just sketch this graph in kind of roughly, but it gets the correct orientation of that linear function. So that's my original. I'm going to label it f of x. Now I want to graph this inverse of f of x. So it's also in slope-intercept form. Just to catch that again, the m here is -9/1, and the y-intercept or b value is 4. So I always start at the y-intercept. I'll graph that point at 4. And then for this one, I want to go down 9 to the right 1. Now I'm in luck here. I can count down 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then over 1 will get me there at 1, -5. And that gives me enough to sketch this inverse. So again, a rough graph, but it does give the proper orientation of this original and its inverse. So that gets us, in terms of our tasks, we've written the inverse, we've graphed the original and the inverse. We just need to confirm now that graphically they show the right characteristics to say, hey, they are a good pair of inverses. And the way we do that is by graphing this line, the identity parent function, which goes through the origin, and then it has a slope of 1. So up 1 over 1, up 1 over 1. And basically it's a corner to corner graph. And we can graph that all across our coordinate plane from corner to corner. Now that's the line y equals x. And the reason why that's important to us is that, algebraically speaking, two inverses, when we compose them, cancel down to the identity line. So what does that mean graphically? Once I put in the identity line, I'm looking for two things. Number one, the original and the inverse intersect on the identity. And when I look here, I see that they are intersecting exactly on that identity line. So it's not a coincidence. It's really a hallmark that they are inverses. The original and the inverse intersect on the identity. So that's the first hallmark characteristic that I got good inverses. The second is kind of a visual reflection in the identity. If I could imagine folding this upper part of the graph, that blue line, over the identity line, it would land directly on top of this red original f of x. Same would be the case if I were to also at the same time fold this red one over the identity. It would hit exactly on that lower part of the blue inverse of f of x. So we got a very clear reflection of the two lines in the identity function. So the second hallmark feature that's in its graphical is that the original and the inverse reflect perfectly over the identity. So let me give a little more room. The original and the inverse reflect perfectly over the identity. And that completes this writing and graphing of an inverse. Let's take a look at another example. So this one that we saw was in slope-intercept form to begin. Let's look at one that's not quite in that form. We'll come to this one last. Here's our next one. So notice that this, it's a linear function for sure. F of x equals 5x plus 10, all divided by 3. And I want to zoom into 100% so we can see that graph clearly. So again, what I want to do is write the inverse. And I don't need it to be in slope-intercept form to do so. So I'm going to start off again by calling this y instead of f of x, just to reduce the clutter in the notation, equals 5x plus 10 in numerator, divided by 3 in denominator. So when I go to write the inverse, I'm going to start again by swapping the x and the y. So the inverse of this function will be x instead of y equals 5y instead of x plus 10. That first step is always the same. And that's all over 3. So again, I've written the inverse by swapping the domain and the range. I swapped the x and the y. And now I need to solve for y. So there's 3 terms here to move, 5, 10, and 3. The one that I will go to cancel first is this 3. So I'm going to multiply the whole fraction on the right by 3. That'll cancel. 3 divided by 3 is 1. And I'll also multiply the left side by 3. So that gives me now 3x equals 5y plus 10. Then I want to subtract the constant. So now we're kind of in the same place as where we were when we started the first inverse writing. That cancels and also shows up on the left. So that now we've got 3x minus 10 equals 5y. The last cancellation here is by dividing the right side, 5y divided by 5. And I'm going to write this because I really want it to be in slope-intercept form to make for convenient graphing. I'm going to distribute the 5 on the left to each term. So I am dividing the whole left side by 5, but then I can split it up to each term. So on the right, that 5 divided by 5 cancels. And this becomes 3 over 5x minus 10 divided by 5 is 2 equals y. So again, the last thing to do is to switch it around so that y is coming on the left side. Y equals 3/5 x minus 2. And that's perfectly graphable now, so I'll box it. I do want to indicate it's the inverse of f of x. So I'm going to call it the inverse of f of x with that -1 power equals 3/5 x minus 2. And I'll box that as well because that is the formal way of writing. This is the inverse of that original function. So let's graph them now. I do want to modify this original slightly. By distributing the 3, we kind of did it automatically when we were writing the inverse. So the way I'm going to view this is as 5 over 3x, that's my slope, 5/3, plus 10 over 3. That's my y-intercept. So I'm ready to graph. I do need to estimate what 10 over 3's value is. So that's 3 point repeating 3's. So 3 1/3. So I'm going to locate that roughly there on the y-axis, 3 1/3. And then I want to use the slope up 5 to the right 3. Now I'm seeing on my graph that I run out of space on my y-axis. So I could put extra marks like we had used on that first example. Just to give you another strategy, you can also count down to the left. I had made that mistake earlier and it does give positive slope. So I'm going to use that strategy. So down 3, 1, 2, 3, in fact down 5, 4, 5, and then to the right 1, 2, 3. So now I can graph that line. I'm going to get rid of these counting marks and sketch that line in. And I'm going to label that as f of x. That's the original graph. Slope of 5/3, y-intercept of 10 over 3 or 3.3 roughly. Now I'm ready to graph that second function, the inverse. So it's a little easier to graph because its y-intercept is -2. If I put mx plus b, overlay that on the equation, so the b value is -2. And then to get the second point, I'm going to use that m value or the slope to rise 3, go right 5. 1, 2, 3. 1, 2, 3, 4, 5. And just like we did previously, I'm ready now to place that line. Let me make sure I catch that point again. It was at 5, 1. And I'm going to sketch this graph in. Let me make sure that I catch that correctly. So if you've got to do it a couple times, that's okay. And on your paper, you definitely use a ruler. I'll label that inverse of f of x. Now that completes the writing the inverse and graphing the original and the inverse. What I want to do now is do the graphical check. So remember, we put the identity line, it's from the origin, counting up slopes of 1. And then it backs up also in a quadrant 3. Let me make sure I get that line perfectly graphed. Okay, and I'll label that as the y equals x or identity line. And we just want to check our 2 hallmark characteristics. So the first is this, that it intersects right where the original and an inverse intersect. So intersection of the identity. And let's label this in the original colors. F of x, the original function, and the inverse. So all 3 lines are intersecting at that one single point at -5, -5. So that checks out in terms of one of the hallmarks that we can check graphically. The other is the reflection. So I can just imagine if I were to fold this left side of the red f of x over the identity, it would hit exactly on the inverse of f of x. Same would go for these parts down below. If I were to fold the blue one over the identity, it would match exactly as it folded with that red one. All right. So again, another example that wasn't in slope-intercept form, but we can get it there so that we can look at the graph and really place the graph easily. Let's look at one last example. So our last example is a special case. And the nice thing about this one is that it's very straightforward and simple to write the inverse. In fact, it's straightforward and simple to graph it as well. So I'm going to start off again by calling this y equals x plus 4, just to reduce the clutter. And then I'm going to make the inverse by switching the x and the y. So my inverse will be in the blue color here. It's going to be x equals y plus 4. Now to solve for y, since that's my next step, all I've got to do is one cancellation by subtraction. So I'm going to subtract 4 on the right. And what that will give me on the left is x minus 4 equals y on the right. And then I'm just going to revolve that equation to give me slope-intercept y equals 1 over 1x minus 4. So I've just put the slope in there. Notice if I don't have a coefficient on x, I can supply the 1 over 1. I can say that that is the inverse of f of x with that -1 power notation. So I'll box that since that is the inverse equation. And now I'm ready to graph. Let's graph the original first. So I'm going to do the same strategy, put a slope of 1 over 1. That's my m. The b value or y-intercept is 4. So I'll place 4 and then up 1 over 1, up 1 over 1. And I could go left 1, down 1 to continue that pattern as I back up down the plane. Graph it. And that is f of x, so I'm going to label it. Let's graph the inverse. So its equation is 1 over 1x minus 4. Same deal here. We want to compare that to mx plus b. So as I locate the y-intercept, that's -4. Its slope is also 1 over 1. So I go up 1 over 1, up 1, right 1, up 1, right 1, continuously across the plane. And then to catch the left hand, you go left 1, down 1, left 1, down 1. Graph it. Label that one the inverse of f of x. So that completes for this, what turns out to be a special case, the writing and the graphing of the inverse in the original. When I go to check my hallmark characteristics and look for an intersection of the original and the inverse on the identity, I don't see one. And that's what makes this a special case. Whenever I've got an original function with a slope of 1, it will not intersect its inverse on the identity line because it's parallel to the identity. So if I use some marks from geometry, the original is parallel to the identity is parallel to the inverse. So you'll know you have that if your original linear function has a slope of 1. We can see the reflection pretty clearly. So if I were to reflect this red one over the identity, it would land directly on top of the inverse throughout its domain and its range. It would cross over there and land directly on the inverse. Well, thank you for joining for 3 examples of writing and graphing linear inverses. We'll come back with some examples about how to write and graph polynomial and radical inverses. But until then, I'll let you go work on your problems. See you soon.